Hello and welcome to this session where we'll be reviewing system responses, so the response by the system to an applied change. So we are trying to understand the relationship between our state variable y and our manipulated variable u. And just a quick note on the terminology. So we said y reflects the state of our process, and we also call that the control variable. So in general, in maths, in a differential equation, we think of the dependent variable y as the state variable. It shows us the state of the system. And in the context of control, we call that the control variable. So the variable over which we want to implement control. And then the manipulated variable u, that is the variable that we are going to use to control our values of y. So we are now trying to understand the relationship between y and u. So we showed in the previous sessions that you could transform this equation into a form that looks like this. So we can get the relationship between y and u. So you typically transform the derivative here into an sy minus y naught. And then you can relate that to the transformation on that side, and you'll get y as a function of u. Then we showed that we could define this transfer function. We just call it a transfer function, y divided by u. And when we work that out, we find a function that is purely in S. So after you divide this equation by u, you typically get a function that's purely in S. So then you have g as a function of S. And the reason we want to do that is because that will really help us understand the response y to our variable u. And an important note here is that this helps us to understand the influence, but it's not exactly control, right? If we are prescribing this function u of t, right? If we are saying, let's apply a step input or a sine wave input or a ramp function, that is not actually control. Typically, we want to set a value for y. So we want to require some value for y, like a y set point. And so we want our state to reach the set point value. And so instead of trying to prescribe some arbitrary time function here, we would rather propose that y is some function of the difference between the set point and our current value y. So for example, instead of just saying u is some step function, so for example, if it's the case where we have the volume control, instead of saying the inlet flow rate was 10 and then we make it 20 and we just hope for the best, instead of saying that, we can say, well, I would rather say that my inlet flow rate must be some function of the difference between the set point, between my desired volume and the volume currently in the tank. So continuing that example with the volume, we want to propose something like this. So we don't know what this function is of this difference yet. But if we take, for example, if we say simply that the inlet flow rate is minus some constant times this volume difference, then that will in effect try to get us to the set point. So if you think about this, if the volume is lower than the set point value, if v is less than v set point, then this number will be negative, and then minus k times that will give us a positive number. In other words, the smaller the value of y away from the set point, the greater will be the flow rate in. So we will want the flow rate into the vessel to increase until v equals the set point value. And if we reach the set point value, so let's say v equals VSP, then this difference becomes a 0, and that means our inlet flow rate is a 0. So when they are equal, then this becomes a 0. If v goes below the set point, then it becomes positive and we start feeding to the system until it reaches the set point value. So that's why we say we want the manipulated variable to be some function of y minus its own set point. So that's what we are doing currently. Now, what we need to understand then is the relationship between the state variable and the manipulated variable u.
Hello.
Okay, now we've got this input here, and so we can see that for this to work well, we will need to choose a good value for k. So you can imagine if you use an extremely large value for k, then for small differences, we will overreact and we will take too large a control action. So you can imagine, let's say we want a set point of 10 cubic meters, and let's say it's currently 11 cubic meters. And if we use a value, let's say of 1,000, then it's going to feed us with 1,000 cubic meters per second, right? Feeding us with a ton per second. And that's probably a far too fast a control action. We will very quickly overshoot the set point value. On the other hand, if we use a very low value for k, then it might take us forever to reach the set point. So there's some optimization to be done. We want a high enough value to get quick control action, but it mustn't be so high that we overreact every time. So we can see there's a fair bit of work to do to get that k value. We can see then that designing this function q in is not so straightforward, and its design will depend on how quickly the system responds to q in. So that's why we really need to understand this. We need to understand what's the responsiveness of our system to changes in this u value. Now, looking back at the work we did last week, we dealt with first order processes. All the processes we looked at were first order, and we saw that in all those cases, our transfer function could take on a form like this. So there was a constant up top, and then as a coefficient to s, there was another constant, and we had a +1. So we could reduce all our first order cases to a form like this. When we found the transfer function, we could get a form like this. And that's quite a general thing to say, that as long as you have a first order process, doesn't matter what the process is, it might be a temperature type of process, a process where temperature is the variable, or it might be level, or it might be concentration. And it doesn't matter whether it's a CSTR or a PFR or some other type of reactor, or if it's a distillation column, none of that matters. As long as the governing equation is first order, we will always get a transfer function like that. So that's already nice and general. Because remember, control engineers are not always chemical engineers. They don't necessarily want to go and derive material balances and so on. So they just want to know, is it a first order process? If it's a first order process, then straight away, they know every important feature about that process. They know that there's a constant, and there are two constants, and one is like a time constant. Remember, in last week's example, we had t divided by tau in all the solutions. So if you don't recall all that, then please stop watching this video, go back to the 2022 Contact 2 video and watch that. Make sure you fully on top of that before watching this video. So this is our first order process. And this is the transfer function. So we've divided out the influence of the manipulated variable. So there's no u showing up here on the right-hand side. It's purely a function in S and these two constants. So what this allows us to do is then say, well, if we want to know what the process is actually going to do, then we can simply get that back by multiplying g by u. And so what's nice about this is we've now isolated out the type of control action we'll be taking. So if we have a step input, then the function u is m over s. So again, be sure to go back and look at why that is. That's all fully derived in the notes and in the videos. But anyway, we'll just accept that. So we know what g is going to look like for any first order process. Now, if we are told we are going to use a step input, then that's what applies. And again, it doesn't matter what the step is, the size of the step is contained in here. So m is the size of the step. And so when we multiply these two things out, we know it's going to be k over tau s plus 1 times m over s. And we showed last time that we'll then get a solution like this. So it's going to be a constant k multiplied by the constant m, so km, and then 1 minus e to the minus t over tau. So that's the other constant. So there are three constants here, km and the tau. And so in this equation, this tells us for any step, for any first order process, this is going to be the governing equation. And so in this nice general form, then we can say, well, if I rewrite this as y divided by km, and if we work with t divided by tau, right, we can look at t as factors of tau. So when t equals tau, then it's a 1, and 2 tau, it's a 2, and so on. Then we get all the possible values here. So this, in a way, is the most fundamental table that you can draw. These are all the values that can ever occur in the system. And all other cases are simply different values of the constants. So if you had some other process where tau wasn't 1, where tau was maybe 10 or something like that, then you can say, oh, for after 10 seconds, then this is y divided by km is this value. So if in your process k and m are 50, then you just multiply by 50, and then you've got the value for y. And so you can generate all possible values for any first order process for any step. So this is nice in general. And besides just having the equation and the numbers, this also shows us that there is only one possibility among all the things that could happen here, right? If you think about this equation, the only thing this equation is ever going to do is to go up exponentially and then saturate at some value. So it's always going to be a curve like this, right? When you look at an equation like this, you realize this is the only possible behavior, that the moment you apply a step in a first order process, it is just going to steady out at some new value. So that's the real reason we want to do these responses. We want to understand what are the possible types of behavior. And when we know that, then we know something about that kind of control. So we know, okay, it's a first order process. Any step is only going to exponentially reach a new steady state. That's the only possible thing that can happen. So let's look at some other things that we could do. We could also apply a ramp input instead. So instead of shooting from one value to the next value, let's say we were carrying on at a single value, and then we began increasing that value as a ramp. So let's have a quick drawing of that. So in the first case, we had simply that we were at one value, and then we step increase to a new value. Now we are talking about the ramp case where we were at one value, and then we ramp increased that flow rate or whatever that is, whatever type of manipulated variable that is. So that's a ramp increase. This is a continuous function, and this line has a certain slope. So that's the gradient of the ramp. In this case, it discontinuously jumps from one value here to a new value, and the gradient is 0 always. So that's the step case, and this is the ramp case. And again, if you look back at the derivation of these functions, for a ramp input, it looks like this. So A is the gradient of that ramp, and then we end up with an S squared for a ramp as well. So again, if we apply this to the first order process, we say for first order, we know G has to have that form. And now we've changed the type of input. So now the inlet flow rate is a ramp. And so we just substitute the function for a ramp there. And then if you follow these developments, so you simply use your Laplace transformation. Well, here first, we are just splitting out the terms. So you can just propose that this form can be rewritten like this, and just that we then have to figure out what these alphas are. So we can work out the alphas, and you'll find then that the solution you finally get looks like this. So this is the solution if you have a ramp input. And if you look at this expression, you've got the constant k, so that k comes from our first order process, and you've got the tau as well appearing here. You also have the a, so the slope of your ramp also appears here, and those are the only constants that appear in this equation. And then if you look at the characteristics of this equation, it is a bit different. So here you have the exponential movement to a new steady state term. But in addition to that, you have a plus KAT as well. So if you can imagine it, you've got the sum of an exponential rise to a new steady state. It's actually like that. And then you've also got another directly proportional to t term. And so if you add these together, then you'll get something which has a high slope here, and then the slope steadies out. So it's something like that. So if you were to plot that out, so here, yeah, in fact, in this case, the exponential is there, depends on what the k is. And well, it's actually because, yeah, it's if you group these together, you can see here. So in your solution, if you group together k and a, then you bring the t in here. You can also say as t goes to infinity, this term becomes a 0. So when you group it together, you'll just end up with the, eventually it will look like this. And so if you use this limit, if you say when t goes to infinity, that term disappears, leaving us with Ka times t minus tau, Ka times t minus tau, yeah. So you can see eventually you are going to get a gradient of Ka, and it's just that you'll be shifted to the right by tau. So that's the solution. Eventually, it becomes a straight line like this, and you will go through a transition period where it smoothly transitions from the 0 to that new line. So you've applied a ramp function. So that's your input. You've applied a ramp function, and then your process slowly moves away from the steady state it was at, and then it eventually ends up with the same, it keeps increasing with the increase of your manipulated variable. So that is something we could have anticipated. We should know first order processes are quite peaceful. So if we keep increasing the inlet, then the process will also start increasing. So we sort of anticipated this response, but now we can prove that's exactly what happens. And again, now that we are able to do this, we can say for any first order process, as long as we apply a ramp input, we can see that we will eventually also start ramping the output, and it will ramp with the same slope as the input. Well, the same slope multiplied by the k, it also has to correct for y itself was corrected by k anyway. So the slope eventually becomes Ka. So we can now understand everything possible for a ramp in a first order process. Now we are going to continue to another type of input. So when we use a sine wave input, we can also understand how the system responds. And you might say, well, why am I now doing yet another thing? Because we could obviously go on forever. We could apply all kinds of input functions, and we could analyze them if we wanted. And where is this going? So the reason that we are looking at the sine wave is actually, we'll find that if we apply sine waves, we learn a lot about the control of the process. So it won't be clear right now why this is important, right? And in fact, it is much more important than these steps and ramps and so on. In fact, this whole section, frequency domain dynamics, right? Frequency, because we are applying a sine wave that has a certain frequency. So we'll see later on, there's a very good reason to apply sine waves. And so that's why this particular form, a sine wave, is important to understand. So we are applying a sine wave at the input. And then if you look up for sine of omega t, you find that the transfer function looks like this. And it's quite surprising, right? If lowercase u is a times sine omega t, and then uppercase in the S domain, if you Laplace transform a sine function, you actually get a form like this, which looks nothing like a sine function. So that's why I say this looks surprising. But again, go through that first set of notes and it's derived fully, and you'll see how we arrive at this from a sine wave. So anyway, when we apply this to a first order process, so there's our first order. Now we've applied a sine wave. So the sine wave has an amplitude A and a frequency omega. Then the function looks like this. And again, we can go ahead and we can propose a form that's a bit more suitable to us, and then determine the alphas or the A's in this case. And if you follow these derivations, you'll find that you get this solution. So it's a little bit inconvenient to work with this. You do have a cos of omega t and a sine of omega t. And if you recall your high school trigonometric identities through some clever manipulations, you can show that you can translate all of this, this form, you can translate it to a form that looks like this. So this is better to work with because we only have one periodic function here. This one has sine and cos. So instead we'll group it all out and we get just sine. Here, we managed to do that by using an offset. So here, this is just cos of omega t and sine of omega t. But when we combine them together, then we get a small offset here, which we call phi. And so now, but this is still a periodic function, right? So, and in fact, I think there's a little t missing here as well. So just check that, please. So anyway, we now have our function that, so yeah, this is omega t, not tau, right? So that's the solution that we have. And so we are saying if we apply a sine wave at the entrance to a first order process, then we also get a sine wave in the response. So we do get a certain period where there's another influence. So you do get a short period, right? This is short-lived because as t goes to infinity, this becomes 0. So this term eventually vanishes, leaving us with the sine wave response. And we're going to look at some of this in some Python code that I've written. So in case it seems to you, well, we're losing contact with the sine wave here because we haven't really shown it. So let's go ahead and apply our, write this up as some Python code.